from South San Gabriel, California, and he attended Cal Poly Pomona for a quarter back in 2017, and then went to community college before transferring to Pomona. So now he's one of the few that can say he's attended both Pomonas. Outside of school, he enjoys DIY things such as fixing cars, and has been cutting his own hair for the past 6 years. But he asks of everyone to not look too closely because you might see some mistakes. Brandon also served in the Marine Corps for 6 years, built sustainability programs while working for the state of California, and worked as an actor. His main interests this next year are going back to the film industry. Give it up to
Thank you so much, Shirley, for the introduction. Once again, my name is Brandon Lau, and today I'm going to talk about scaling limits and the Feynman-Kac formula. Observe what happens when sunbeams are emitted into a building and shed light on its shadowy places. You see a multitude of tiny particles mingling in a multitude of ways. Their dancing is an actual indication of underlying movements of matter that are hidden from our sight. It originates with the atoms which move of themselves. Then those small compound bodies that are least removed from the impetus of the atoms are set in motion by the impact of their invisible blows and in turn can against slightly larger bodies. So the movement mounts up from the atoms and gradually emerges to a level of our senses so that those bodies are in motion that we see in sunbeams, moved by flows that remain invisible. Humans have been theorizing about atoms and particle behavior movement for thousands of years, and today I would love to talk about an introduction to diffusion, a microscopic origin of diffusion, a framework for convergence, solving differential difference equations, and talk about future directions for the project. To start off, the diffusion equation in the real setting is the partial differential equations as follows, and the fundamental solution to this is given by equation 2. Now, this was solved by Joseph Fourier with his theory on the heat equation, but one cool thing about it is that there's actually a very deep mathematical analog between a whole family of these differential equations. And some of them include the diffusion equation, the heat equation, Schrödinger equation from quantum mechanics, and also Black-Scholes equation from finance. Now, I personally feel like thinking about particles is a little more fun than thinking about finance, so we're gonna stick with that. To give everyone like a better visual perspective of what this means, from a macroscopic perspective, imagine, it's cool because you can see this phenomenon on a day-to-day basis. Imagine like you're milking your coffee, or in like our case, this dye in water. Initially, the dye spreads really rapidly into the water, but once it starts getting towards the edges and the corners of the water, it slows down rapidly. Now, to get a better idea of why this happens, let's look at it from a microscopic perspective of a single particle. I don't know about you, but to me, this kind of just looks like a random movement where there's like a pesky fly like trying to eat your food. But what's cool is if we see it from a sub-microscopic perspective, these type of random movements are actually caused by collisions on the particles, as Lucretius said in the quote. This is really cool, and like Einstein did a lot of amazing work with Brownian motion on this, and I would highly encourage people to check it out if they're interested. Now, this is going to be our motivating question. Is there a mathematical framework that can capture this type of relationship between the macroscopic, the microscopic, and the submicroscopic? And if so, how is it useful? To start, we're going to talk about the microscopic origin of diffusion. We're going to take x tilde to be an abstract random variable with the following distribution, where x tilde has half a chance of going to the -1 or half a chance of going to 1. Now, think of this as like a fair coin flip, where there's half a chance of flipping heads or half a chance of flipping tails. In addition, we're going to let this x tilde sub I be a sequence of these abstract random variables that share the same type of behavior and distribution. To give everyone a little better of a visual idea of what this means, we're going to look at something called the random walk. And I like the name more of a drunkard's walk. It's pretty fun. So x tilde, let x tilde be almost surely equal to 0. And we're going to denote another s tilde to be the sum of that sequence of x tildes. And what's cool is we can see from like a symmetric random walk on z's that like if we're starting at z or 0, we have like half a chance of going to the left or half a chance of going to the right. So eventually you get this type of motion where it's like, oh, what's going on? And that is where our random walk comes from. Now we're going to look at this time and space scaling sequence. So a sequence of space scales, delta, is a strictly, hi Teal. A sequence of space scales is a strictly decreasing positive null sequence with delta not equal to 0, 1. I like to think of this as like your step size almost. So like if you're taking a full step, it'll almost be equal to 1, but as we're scaling it with this type of delta function, it's almost getting like smaller and smaller and smaller. And similarly, we have this type of time scale sequence with tau, which is also a strictly positive decreasing null sequence, and where tau not is equal to 1. I kind of like thinking about this in a perspective of like almost like timestamps, where like if tau not is equal to 1, you're almost like taking a timestamp of like every single step. But as like the sequence is like getting like smaller and smaller, it's almost like taking a timestamp of like half a step, and then like a quarter of a step, and then like so on and so forth. So it gets smaller and smaller. Now we're gonna have a sequence of spatiotemporal embeddings, which takes this type of like timescale concept and space scale concept, and we're gonna define it as iota. So iota takes in that type of step, number of steps, and the sizes of the steps. Yeah, and then like it scales it accordingly with tau and delta. So now we're going to look at something with the variance of S tilde. We're going to define a new Y tilde to be a scaled version of this S tilde as follows. And the calculations show that the variance of S tilde is equal to n. Now, when we scale this type of S tilde sequence, the variance of Y tilde is actually equal to delta squared times the floor function of t divided by tau. What's really cool about this is by observing this type of variance of Y tilde and assuming as the limit m goes to infinity of delta squared divided by tau is equal to 1, we actually get a relation between delta and tau given by delta squared is equal to tau. Now, that's going to be very important for the next slide, and I'll mention it to everyone. We're going to denote another thing, PTX, as a probability mass function for Y tilde, where a particle starts at 0 and is at a position x and time t. Given this, we're going to denote this equality as follows in 11. And what's really cool about this equality is the fact that this is really built off of that type of random walks where there was that half a chance of taking a step to the left, or like half a chance taking a step to the right. And if we divide PTX and tau on both sides and do some manipulation, we get the following equality. This is super cool because then this is actually the discrete version of the diffusion equation we were looking at earlier, where you can see on the left side it's almost like the definition of the first derivative in respect to tau, and on the right side you get almost like definition of the second derivative in respect to like a delta. But now this brings us to an additional question. Is there like a more precise connection between this matter? To start, we're going to talk about this framework convergence. We're going to talk about we're going to label I to be a continuous time interval of the form from 0 to t or 0 to infinity. And we're going to denote f of I to R as the space of all paths in R with domain in t. I just like to think about this as like basically like all paths for future reference. Now we're going to go over a little bit of the path space terminology. So a set omega is a path space of R if there is a time interval I such that omega is a subset of the set of all paths going from I to R. Bear with me, there's a few of these. An epoch for paths in omega is a strictly increasing positive finite sequence that is I valued. A route for paths in omega is a finite sequence of Borel sets of Polish spaces S. A history is really cool because then like it basically takes element of the epoch and element of the route and it pairs it up as followings, where like the T's are the like epochs. I like to think of them like more of like the times, and then U's are the routes, which kind of like think about it as like almost like events. So now we're gonna look at more terminology, everyone's favorite. For any history H, we're going to denote E of H as the epoch associated to H, and U of H as the route associated to H. We're going to let L of H be the number of places of the epoch of history, essentially the length of the history. Now the collection of that is going to be denoted as big H, where it's like the set of all histories for the path space omega. Now, we're going to define a new function C to be a function from this type of big H up to the power set of omega, and define for each little h in big H as the followings. This is really nice because then like this C of H is actually like a simple cylinder set, and using the set C of big H, we're gonna have the set of all cylinder sets, simple cylinder sets. We're gonna use this for the following. So the set of the cylinder sets is a sigma algebra that is generated by all these little ones right here. So this is gonna be important later on in the process, but first off, we're gonna consider the probability of C of H. So we're gonna take rho to be the fundamental solution to the difference equation. And then for each little h, for each history in big H, if u naught of h contains 0, then we're going to divide p of c of h by the following integral. So this basically essentially takes almost like small like time space and also a time and then like a space, and then it gets like the probability of each individual increments, and then like the collective of it gives us the probability of c of h. And otherwise, the probability of c of h is going to be equal to 0. So now the great thing about p is like the function p can be used to build a probability measure w, which is going to be a Feynman measure later, on the sigma algebras. Now we're going to define our last function y on the continuous time interval and the set of all path spaces going from I to R with following the 17. What's really cool about this is this essentially gives omega of t, which is like a value for the path space. So if you want to like see how like or what we're essentially doing with this function, we're really just going to be incurring like the t and the omega into the y in order to get this type of like value for the path space at time t. Now, what's really nice about the three functions that we just made is that with the we can define a stochastic process with this. So with the three elements of the set of all path spaces going from I to R, the probability measure that we just had, and like this y function that gives a value for the path space at time t, we can use this to define a stochastic process. And there's a version of this in the space of continuous paths C of I to R. So now, in a similar sense, we're going to take the probability measure P that's associated with ym, and the paths that are initially going from the set of all paths going from 0 to infinity to R. And we're going to denote E to be the expected value with respect of the measure P. So if we have like a T1, T2, T3, and that's an epoch, then we have the following inequality. What's really interesting about this inequality is that we're essentially taking those type of like scaled S tildes, and then like it shows that there's actually an upper bound to them with the scalings of like the deltas and the taus. And what this actually implies is that there's a version of this in the sample space of E from 0 to infinity to R. So this is basically going to be a Skorhawk space, which is like the set space of like Cadillac functions that are left limits, right continuous. Now we're going to refer to our y once again and our measure p, and we're going to look at we also want to note that that type of like continuous space from 0 to infinity to R is a closed subset of D from 0 to infinity to R. And we're going to view W as the measure on the Skorhawk space, the Cadillac functions. Now, this is going to be a very big theorem. So what we actually end up seeing is that our measure P converges to the Wiener measure in the following way. For like any bounded continuous functions of Cadillac functions going from 0 to infinity to R, we get the following theorem. This is really cool because then what this essentially means is that just by scaling that type of like probability measure from our random walks, we actually end up getting the Brownian motion is actually a limit of those type of like random walks that we scaled early on. So that was a lot of like the math behind it, or yeah, there was a handful of like terminology in math. So I just kind of want to give everyone like a visual idea of what this like implies. So on the left, there's missing like some of the dots, but then like these are essentially like that type of like random walk behavior where we're talking about where it's like stumbling to the left and stumbling to the right. And then on the right side, we have like this type of like Brownian motion that's kind of like a collision of like just like 10 particles where we saw early on. If we actually use those type of space scales and time scales, we'll see that they start emulating this sort of like similar behavior and characteristic. And then if we simulate this for like 1,000 paths of the random walk and the Brownian motion, you can see a lot of the similarities. I would like everyone to note that like this type of Brownian motion, it still seems like there's a lot more of like variance compared to like the random walk. And this is why concept of convergence is going to be very important for if we actually wanted to go from the random walks into the Brownian motion. Now, this brings us to the Feynman-Kac formula. So for a wide class of functions V, and for like a nice enough continuous function f, we have the Feynman-Kac formula can express any solution u of the initial value problem as the expected value of the following. So we're gonna trace back to this formula real quick, but what's really cool about this is, in a similar sense, we have like a discrete version of this Feynman-Kac formula that solves any sort of discrete initial value problem, and this is the solution to that type of like partial difference equation. So I wanted to just kind of put them like side by side to each other because I skimmed over those really quick. But like you can see some of the similarities where like the Feynman-Kac it uses like it goes in the continuous spaces, and then like in discrete settings it uses kind of like the Skorhag space or the Cadillac functions. And what's really cool about this is that if we use something called like the Donskis invariance principle, we'll actually see as the limit m goes to infinity of this umtx, it equals utx. So for future directions of this project, I would love to investigate more of these like PDEs in the p-adic setting. And then I would love to also code more functions that take in that type of like time scale and like space scales to simulate and visualize more of this. What's great about this is because, or like especially with the convergence of UM to TX, is the fact that we can work on the continuous setting and the discrete setting, and both have their advantages and disadvantages. So a lot of like natural processes, like especially with the diffusion equation and heat equation, they're much more of like a continuous like phenomenon. But then like they're much harder to like either code or visualize because like it's a handful computationally. Whereas like on the discrete side, it's much easier to visualize or like kind of simulate to kind of get an idea of what these type of like partial difference equations look like. And also some of the processes like even like population growth, like those are very beneficial when it comes to like the discrete type of like one step at a time. But that I want to give like a special thanks to Adam because he's been so patient with me like the whole time while we're working on this thesis. And like all the like math professors, like I've learned so much from every single one of them, and especially with the math community. Math coordinator Will right there, I know he's peeking in the corner right there. And some of my like math friends I've learned so much off of, like including Robin, Tilo, Rio, especially working with like Kyle and Anna, like they really saved my life. So thank you so much, everyone. If you guys didn't like math, then like you can just play around with diffusion with Skittles.
Yeah, I have two questions.
Yes.
The first one is, how did you embed GIFs in your Beamer?
Pardon?
How did you embed GIFs in your Beamer?
Oh, so I use like something called like I think like graphics, and we can just like include like images. I can show you like the code in like LaTeX, and it is kind of annoying because you have to like get like a GIF and then like kind of cut it into like different frames, and then like it just plays it frame by frame.
So it's like different PDF pages.
Yeah, so it's all like PNG files, so it's kind of like
Okay.
after you figure out the first time, I think it's more worth it, but like I kind of regret spending that much time.
Sorry.
Oh, sorry. Second question.
Yeah. Are there any physical interpretations for the p-adic diffusion? Because for this diffusion, for this equation, you can interpret it as diffusion, but in the p-adic setting, is there any physical interpretation?
That's a great question. So I don't know like anything like particular about the p-adic setting. I just know that like the formulas can be very useful in terms of like the physics context, right? But like I would love to investigate that more in the future. I'm sure like a lot of the professors would know a lot more. So I'll guide you to the right people.
Okay.
Yeah.
Oh, so at the very end, you said that you could do these experiments. With
Yes.
Skittles. Yeah, have you done some of these experiments?
So I really haven't. The main thing I really did was like simulating this random walk in R, and like I think this was like much more simple. But then like the things that I kind of really want to like simulate more is like as you can see like with the formulas with like the partial differential equations, how there's like these type of potential terms and everything. I would love to see like how they visually change as we have like that type of like potential values, like different like initial values.
All right, well, thanks, Brandon.
students, just remember there's a sign-up sheet somewhere around here, so if you can sign up, please do so. Otherwise, I'll see everyone in 2 weeks.
Thank you.
So the point is about PI, it's a non-Archimedean local field. So what that means is it's like think about it as a ruler, right? Physics measure stuff, right? At some point, if you make the ruler small enough, you can't measure stuff, right? So that's the physical interpretation of like why you want to put something in the PI. Really, what we're interested in is like non-Archimedean local fields.
Robin, thanks for texting me.
So
Yeah, no worries.
thinking of looking at that.
I was like, where's Timo?
Sort of framework.
Wasn't there like 2 months ago? Did you have any?
Yeah, it's a